Hi guys! Today we're going to be talking about related rates, which is a Calculus 1 concept, and this is a pretty common question that goes on tests. You've probably seen problems where there will be a ladder sliding down a wall, and you need to figure out the rate that the ladder is sliding when it's at a certain height. And so today I thought that we would do a less common problem using a cube that still uses these related rate concepts, the same techniques that you need to use to solve the problem. Two smaller concepts that are folded up into related rates are implicit differentiation and geometry. Implicit differentiation means that you need to take the derivative of a variable with respect to another variable. So the derivative of volume with respect to time or area with respect to time. And geometry means that depending on your teacher, you may or may not be given a formula sheet. So if you get a problem like this on a test, it's important that you know what is the formula for the area of a circle, for the volume of a cube, Pythagorean theorem. These common geometric formulas are going to be important for solving these problems. So let's get into the problem. The first thing that I like to do is I like to make a sketch of the situation, and I like to kind of lay out the information that is given to me. So volume of a cube, so I'm going to draw my little cube here. It's a little messed up, but that's okay. This just kind of helps me orient myself in the problem. And then let's take a look at the information that we've been given. So we know that we're talking about a moment in time where the length of one of its sides equals 8 inches. And since this is a cube, it means that all of its sides have the same length, so every side is going to equal 8 inches at this moment in time. The next thing that we know is, and I'm going to underline these in color so you can see where I'm getting this information from. The next thing that we know is that the volume of the cube is increasing at a constant rate of 6 cubic inches per week. So that means that the derivative of volume with respect to time is equal to 6 inches cubed per week. Every 1 week, it's increasing 6 inches. And we can pull that information out by this constant rate phrasing. And the final piece of information that we're given is what we need to solve for. So what we need to solve for is how quickly its surface area is increasing. And so that's going to be finding the derivative of the surface area with respect to time. So my next step is going to be thinking about those geometric formulas that I talked about earlier. And for this problem, we're probably going to need the formula for the surface area of a cube, which is 6 times L cubed. And I wanted to mention that I'm using this cursive L shape, and I used it over here with the length equals 8 as well to differentiate from the number 1. And another formula that might be useful is the volume of a cube is equal to the length cubed. These are common geometric formulas that you should know. So the first thing I'm going to do is I am going to take this volume equation and I am going to differentiate it with respect to time, because I have this concrete piece of information that dv dt is equal to 6, and I would love to have somewhere to put that information. So if I take the derivative of volume with respect to time, I get dv dt. If I take the derivative of L cubed with respect to time, I'm going to use the power rule, so I get 3L squared, and then I need to multiply by dL dt. And if you're a little bit confused about why I have this dL dt there, go back and review implicit differentiation, but basically if I'm trying to differentiate something with respect to a variable and the variable is not the same on the top and the bottom, then I'm going to have to keep this differentiation symbol around. So I know that dv dt equals 6, and I have 6 is equal to 3 times 8 squared. And just as a reminder, that 6 comes from the information in the problem, and that 8 comes from information in the problem as well. And we still have it multiplied by dl dt. There was no information in the problem about the rate that the length was changing at one time, so we have to leave that. And we can go ahead and solve for dl dt at this point. And so we're going to have 6 divided by 3 times 8 squared equals dl dt. And we can go ahead and simplify that fraction to, let's see, 0.03125 is equal to dl dt. All right, so that's as far as I can take this chunk of the problem, but we've still got this surface area, and since we're looking for the surface area increasing, it would be a good idea to differentiate this top formula and be able to get that rate. So I'm going to take that over here, and I'm going to differentiate this equation as well. So the derivative of the surface area with respect to time, and I'm going to use the power rule again, so I'm going to get 12L, and then if I differentiate L, I get dL dt. And again, I'm going to highlight where I'm getting some of the information that I'm going to put into this problem. So I don't know dSA dt yet, but I do know my L, so I can say that that's equal to 12 times 8, and we actually solved for dL dt in the previous question. So I can take this and plug that in right there. 0. So now all that's left is some pretty simple algebra. So I'm going to pop this into my calculator. If you're not allowed to use a calculator on your exam, it is perfectly okay to leave your dL dt in this fraction form and I would simplify the 8 squared, but you can leave it as 6 over 3 times 64, and then just put that fraction into your DLDT and multiply out your fraction and get your answer that way. Ask your teacher how they want their answers formatted, but that's what my teachers have accepted in the past. So when I do this 12 times 8 times this decimal, I get 3. So derivative of surface area with respect to time is equal to 3, and it's super important that you have the correct units here at the end. Since it's surface area, my units are going to be in inches squared, and it's still going to be in 1 week because that's the unit of time that we got at the top, and that's what we have to carry through. So this right here is my answer to this related rates problem. It looks really scary at the beginning, but it isn't that bad. I would say just play with it. Write down the formulas that seem to relate to your question, like I did with this surface area and this volume equation. Differentiate them, put the information you know into them, and keep playing with them and see if you can get an answer if you're really not sure where to go. The biggest mistake that students make on these kinds of problems is forgetting that you need to keep this derivative when you take the derivative, because you're so used to taking the derivative with respect to x and making that kind of disappear, and you got to remember to keep that around. That's going to be the key to solving these problems. So I hope that helped, and good luck with related rates.